So if this seems like death by PowerPoint, I apologize, but we'll get our hands on some stuff tomorrow morning, and again, the more questions, the better. And I've got a very short bit on microalgae to finish up now on culture management strategies, and I know I've already talked with some of you about the options and the pros and cons of different ways of managing cultures, but I'll go through a bunch of examples, and one of the messages is there's actually nothing new in microalgal culture, and by new it's like by the mid 20th century, pretty much everything that could be imagined has been tried. So, and then I have the rest of the afternoon about bivalve nutrition, and that's going to be in a few chunks, and again, the more questions and the more discussion we have, the better. So, when you grow something, you try to provide the perfect environment for it. So here's some thoughts about that. For keeping stock cultures, these are examples from our laboratory. We keep everything in enriched natural seawater. It's sort of 2F. Very high nutrient in 125 ml flasks. They're sterilized in an autoclave, and aseptic transfers from one to the other. About every 6 weeks, they have to be subcultured. It's half an FTE, half a full-time job. Yeah. Yeah. It's called E-Medium. It was invented by my old boss, Rene Euclides. It was published in Handbook of Phycological Methods, Volume 1, the Janet Stein book. Right. Yep. It's just surface seawater from Milford Harbor. Then we have everything in test tubes in completely artificial seawater, Luigi Professoli's ASP2. That everything in our collection, we have 130 something strains. Almost everything, actually. There's a couple of things that won't grow in that, but and that's a medium that was formulated in 1940s, I think. There's no seawater in it. It's all reagent chemicals. And then we have everything on agar. This is a great way for hatcheries to keep algae off season. It's just whatever culture media you use, 1.5% Bacto agar. You boil it on a hot plate to dissolve the agar. You distribute it into test tubes. You autoclave the test tubes or sterilize them, however you sterilize, and then you let them cool on an angle. We just use a block of wood and put all the racks on an angle, and you get this slant thing going on. And then the first time you establish an agriculture, you leave them at that angle in wherever you incubate. You pipette a couple of mil onto the surface. You do that 2 days later again, and you get a little lawn of algae growing on the surface of the agar. After that, to subculture them, you only have to do it once or twice a year. You scrape a little off with a sterilized loop, and you paint it on the next slant. So again, you only have to subculture them once or twice a year. What limits that is the agar dries out and cracks, but the algae stay viable that way. A really good option. Oh, and the Fernbach flask here is how we aseptically get algae from the collection into our research quality carboy cultures, and that's what's pictured here. They're 5-gallon bottles, not anything that nobody's familiar with. We do two things differently. We maintain aseptic conditions in these bottles, so the culture media is sterilized. We have a way with flaming and stoppers and sterile pieces to get the culture in. I'll say a lot more about culture management in a little bit, but we operate these semi-continuously. So we harvest half the volume into the bottle here, replace that volume from the bottle here without introducing bacteria, and the rest of the apparatus is there to get air and carbon dioxide in without contaminating with bacteria. This has been operating since like 1970, really dependably. So it's but it's it's $400 a dry kilogram to grow algae this way, which is not good for business, but for research projects, if you need pure algae, for biochemistry, for we work a lot with with chemists and so on that need pure biomass, and then our own experiments with probiotic bacteria, for example. If we had an unknown bacteria component in the algae, we wouldn't be doing good science. But it's really not a farm scale kind of thing. Yeah. Yeah. So again, the media is about 2F. So for T-ISO, we're like 20 million cells a mil. Tetrasomas for about 7, 8 maybe, because it's a much bigger cell. Diatoms like Ketoceros are 15 million per mil, something. So again, it's just different concept than farming. It's a research application. And a kind of unfortunate thing. Euclid's published most of this method in 1973, and a lot of hatcheries try to follow it, and it's really not a good idea because it's expensive and unnecessary. So what we've been doing at larger scale is here, and there's a couple of things I talked to people about already. One model we have is flat open tanks, and what you're looking at here is a little motor and a stem, and there's a foil down here. We mix the cultures when we can. It's that shape of culture. We mix them with a foil that allows the algae at the bottom that are in the dark to get up to the surface, to get some light, to get some carbon dioxide and blow off their oxygen, and then get pushed down the middle again. So it's a circulator. I mentioned bubbles are evil. I'll tell a little bit more of the bubble story now. The way an oil slick forms on the surface of water also happens in a bubble, on the surface of a bubble. And that oil slick is in fact fat, and a dense microalgal culture leaks a lot of fat and a lot of organic material. That all absorbs onto the bubble. If the bubble is small and it dissolves, it condenses to a colloid. That colloid is substrate and food for bacteria. So it really encourages bacteria. The bubbles that break at the top, you say, well, that's good. Well, they make aerosols that fall back again into the top of the culture, and those aerosols dry in the air and become a colloid. So no matter what, you're producing a substrate and food for bacteria if you bubble a culture. So our biggest cultures, that are that shape are not bubbled. They're mixed physically. I'll show you another picture in a minute. And then the tube cultures, we have no option but to bubble them, to stir them. We tried some stirrers and they didn't really work that well. So we actually only use our tubes to amplify biomass from indoors. And our production cultures in our greenhouse outside were, before they were destroyed by a storm, were these 20,000 liter tanks. And the project here was to address the cost of algal culture. So we're in a greenhouse because that $400 per dry kilogram indoors was about 95% the cost of running the lights. So if we use solar energy, we figure we get almost an order of magnitude improvement. In our open tanks indoors, because of artificial lights, was about $300 a dry kilogram. And we did it. We got this down to $30 a dry kilogram, growing Tetraselmis and some diatoms, Ketoceros and Skeletonema. Where we are latitude-wise, day length is too short, and I'll show you some great data from Shannon Misek, the chemist in our group, and about why you need to add artificial lights up in our latitude. You may not need to do that here. I'm not sure how. What's your shortest day? How many hours of daylight? Okay. You're probably okay, because we found 8 was the magic number, and we have a month and a half below 8. Okay. Yeah, there is actually. From a gas transfer, the surface to volume of a small bubble is better, but more of those bubbles dissolve, and that's more of a problem actually with the colloid formation. So actually big bubbles are better for mixing. They're not as good for gas transfer because the surface to volume is smaller in a big bubble. But still, practically speaking, if you have to mix with bubbles, bigger bubbles is better. So we actually, we have not a diffuser, but a chunk of PVC into which we've drilled like 2 holes, of a certain size that make a certain bubble.
Bigger bubbles than that.
Yeah.
Also, your bubbles are going to expand in a long tube. When you have a good size bubble to start, you have less and less pressure, so the bubble will expand as it goes to the bottom, giving you a better drag and a better movement of the body.
Yeah, that's interesting. We never actually even thought about that because we're usually not traveling through, much of a column. Those are, 2.5 meters tall, the tubes. Yeah. Good point. Again, we never really thought about that. There still is, we still get accumulation of stuff down in the bottom, and more recently we bought these with cone bottoms that that help that, because you can put the diffuser right down in there. Yeah, I hate them. Yeah. Yes. Yep. And we put these tubes in because that's what our industry uses, everyone. And I try to find a way to make them work, but they really don't. So the new thing we're doing now, we just started building this, is bags on the side. In a kind of a wooden thing, and they're tipped up a little bit, and you stick the air in the bottom, and it makes a bubble that grows until it overcomes the friction, and that bubble travels. One bubble travels up. Yeah, and makes it so, and that's already being used in a bunch of places. We just are putting it in to demonstrate to our industry that this is an option they ought to be thinking about. Yeah, so I said we got down to $30 a dry kilogram here. In Milford, Connecticut, the cost of land was like 30% of that, because it's really expensive. It's a very shishi town we live in. So if you were to do this in someplace where nobody wants to live, it would be more cost effective. And it's hard to find a coastal place that nobody wants to live. So it's, oh, good discussion. Any more on this? I have a bunch of photos. As I said, there's a lot that's been tried over the years, from very elaborate bioreactors. This is a company, Coastal Biomarine in Connecticut, made this thing. People use plastic bags hanging. This was very highly developed in Israel in like the 1960s. Some people are still using it. This is the most complicated little bioreactor I've ever seen. It did amazing things, but it would make 100 milligrams of algae a day or something, so it's not very practical. And then these things, which are no better than those tubes I showed you. Light penetration and mixing are very difficult in that shape. It's a terrible shape, because what you really want is a big surface area for light. And if that surface is a hard surface, things will stick to it and it'll get dirty. If that surface is the surface, you can mix it out, right? And so I mean, those 20,000 liter tanks with the foil, from our standpoint, for the simplest culture, for mass culture in the tens of thousands of liter approach, that would be our favorite. I'm trying to wean our industry off these standing up bags and wire baskets, because you can't mix them, and light penetration is always a problem. Yeah.
If your big flat ones you have good surface to volume ratio, you have a mobile cell like a isocrisis, and you could interrupt the phototaxiation, but as far as oxygen is concerned, couldn't even really need that much aeration or movement.
Yeah, but again, you got to move them relative to the water. You have to help them. They're not going to swim enough, and then again, right? You could get a written affidavit from each cell that it will not swim toward the light, but they're not going to respect that. So I mean, you really have to work with the organism and its peculiarities. Tetraselmis is, I don't know how many of you grow tetraselmis of some kind. Yeah, so that is a super interesting organism, because it lives in tide pools and right on the fringe of the sea, and it has got an attached phase. It doesn't stick because something is wrong with it. It sticks as part of its life cycle, because when the tide goes out, it doesn't want to get washed out to sea. It needs a way to stay on the fringe of the sea, so it attaches with a little stalk. And if you put a lighted surface, you put Tetraselmis in a culture with a lighted surface, that lighted surface is going to be coated with Tetraselmis on little stalks before you know it, and the light won't get past them. So, you know, it's a difficult, it's a wonderful organism, but it's a difficult one to really mass culture well, unless you have a culture situation where the lighted surface is not hard. It's the surface of the water. So, you know, that's in our greenhouse, that was our star performer, because we were working with it. It could stick on the sides, it could stick on the propeller all it wanted to. It wasn't impeding the function of the culture. Okay, so here's some hilarious historic attempts at working with theory. I mean, you know, it makes sense. So here's an algal culture apparatus on a little wheelbarrow. So you could move it from the shady part of the lawn to the bright part of the lawn and take advantage of full day sunlight. This is a graduate student somewhere in Asia mixing an algal tank. Those of you who are graduate students can, you know, I'm sure relate to that. And here's using the theory, which is true, that the closer you are to a source of light, the stronger the illumination. So if you lift the part of the, 20 feet in the air, you're that much closer to the sun, and it's going to be that much more efficient, right? But I mean, so, you know, in a way, can you argue with the theory behind any of this stuff? No, not really. But, you know, practically speaking, again, like, you know, not everything, not every theoretical idea is great. And we were talking earlier about LEDs. And there's, you know, a lot said. I don't have anything in this on LEDs because in my view, there's not enough science for a consensus on like how to use them. But, you know, I've been to so many places that have, you know, a perfectly matched ratio of red to blue LEDs to match the chlorophyll A uptake. And every one of them is thrown in the corner and turned off. And they either have, you know, full spectrum tube type LEDs or, you know, sodium vapor, or they got the white LEDs and they tell me, well, you know, we bought the ones at Walmart, they didn't work, with the ones at Target work great. So, you know, there's still a lot to be done on that, but like, don't assume just because the measures that we use for lights for residential and industrial applications are all based on reflectivity and our ability to read, not on photosynthetic energy. So, you know, you remember that slide way back with all the absorption curves of all the pigments. You know, you have to cover that whole spectrum, actually, for different microalgae, and different microalgae have different spectra that they need. There's a guy in France growing chlorella on all red lights. But that's all they need. They only need the red lights. You know, I said, well, what about other things? Nobody else, nothing else will grow like that. So, you know, there's a lot of specifics too. And so somebody, you know, publishes something or has experience growing a diatom with one kind of light, you may not be able to grow Tetraselmis with it or something else. It's just, again, getting from theory to practice is not always a straight line.
So we're safe to use in the summer?
Yes, but not too much. Yeah, you know, that was, you know, again, the cost of solar is the cost to own the land. How many photons fall per square meter per day is, you know, is what you have to pay for. So that's why we could save, you know, 90%, you know, or, you know, almost 90% or more than 90%.
So you basically, you can calculate how many algae cells you can grow strictly by the surface area and the amount of photons that are hitting it?
Yes, we did, in fact. We actually funded a graduate student at University of Rhode Island to write a factory software that included that, you know, basically factory control software, and gave us the parameters under which we could operate at our latitude in terms of, you know, photons, the efficiency of their use, what percentage are absorbed, you know, and what percentage of that goes into sugar, what percentage of that grows how many algal cells. So yeah, we made it. It was a spreadsheet based thing. It was like pages and pages, you know, back, but in the front end, we could just put, you know, raw data in and get production stats out. So here's some stuff that actually works. I don't know, has anyone been to like a really big microalgal farm in Hawaii or California or Israel? Or this thing? Yeah. Yep. So, this takes principle and makes it work. These are great big, usually oval shaped raceways, and they've got a paddle wheel, and there's actually a high point right at the paddle wheel, and the paddle wheel lifts the water over a little bump, and then the water flows downhill back to the other end, and then lifts it again. The first one I went to was in Hawaii at Keaholey Point, and they were growing Denaliella, a green alga that makes a lot of beta carotene, and they were selling the biomass to a vitamin, like one-a-day vitamins, to extract the beta carotene. So if you take a one-a-day vitamin with, beta carotene as one of the components, probably came from Denaliella in a culture like this. But it's this deep. It's breathtaking. It's like the size of a football field. It's that deep. That's it. So it's very dense. The bottom of it is still dark, but it's moving, and they have bumps all along the way, like that. Remember the slide I showed you of the boundary layer physics? They put bumps there to keep it mixing the whole way around, and they operate these semi-continuously or continuously. Most of them, they just keep harvesting biomass and adding water and nutrients, and these things go. So I mean, that again, uses theory and engineering to make a system that actually works. It takes a special organism and a special place for this to work. Denaliella works especially well because the pH can rise up to 10 or something, and for some reason it still functions. It's got another set of enzymes to help it get get carbon and get other nutrients. So is something of this scale good for a shellfish farm? I've actually been to shellfish farm, one in Europe, that had a raceway in a greenhouse. It's a pretty big scale. They were growing bulk algae. Yeah. Yep. So here's the culture management choices. How many people use batch culture? Almost nobody. Good. Because this is where you inoculate a full culture container with algae. You let it grow, you harvest the whole thing, you wash it out, you refill it, you start again, and it's very labor intensive. It's not terribly efficient use of space because you got the downtime here and here. But in our region, almost everybody uses batch culture, and they say, well, we probably could do better, but this works for us. So and one of my campaigns when I do the microalgal culture workshop in my lab is I try to get people off of batch culture. So most of you are off of that. So let's see. Here's the advantage, though, of batch culture is this is number of cells and this is time. So you put an inoculum in. There's a lag phase while it gets ready to grow. It actually, remember I mentioned siderophores, those chemicals that are released to allow them to acquire metals. They have to condition this water. The algae you put in it have to condition that water so that the metals are available. And then there's mitotic division, so log phase growth. Then there's a stationary phase, and then you get a decline that can be slow or really fast, depending on what you've got. So what batch culture allows you to do is decide whether you're going to harvest the cells while they're growing exponentially or give them some time in a phase when they're not dividing any longer, which can be a benefit or a detriment depending on your application, but you have the choice. Okay. Yeah.
Have you seen a nutritional discrepancy between the height of log phase and your static or prior to crash in the nutrition profile?
You're I don't know, probably about 10 slides after me. Okay. Continuous culture is continually replacing the harvested portion of the culture. So it's just a stream or it's like a lake, and we all know, or a pond, we all know how productive ponds can be, right? So nature has, has developed this pretty well. Their advantage to this is that the production should be very predictable based upon some things that you have control over. So you need to know the growth rate of the cells, and the maximum growth rate they might have, the concentration of limiting nutrient, and the half saturation coefficient of growth. And you should get a very predictable harvest out of a continuous culture. So the theory is elegant, as I say. The reality is a bit more messy than that, because this equation depends on absolutely constant conditions. So if you're in a room, in a clean room with, you know, the light, the temperature, everything, nothing changes, it should run pretty well. But nevertheless, it's one of the things I did in graduate school. Actually, we ran a bunch of these equations with a little tiny perturbation in one of these inputs, and plotted using MATLAB. And this is actually data from one of those that I ran for T-ISO. So you put a tiny perturbation in, and things tend to go kind of into a cycle. And sometimes those cycles go near to extinction, so you can almost wash out your culture, even though you're doing everything right according to this. So, you know, again, the theory's great, and, you know, I know there's people that use it. The way to make this work actually is to slow everything down. And that way you never fall down here, but you also don't achieve the production potential of your space. So you run everything so slow that it can't possibly not catch up to the bumps. So, you know, that's most people. I don't know. We're gonna have a discussion later. I'm really interested to know how you guys are managing that. But, you know, that's kind of the people who have the continuous bag systems that they bought from John Bayes. You know, his protocols run them really slow relative to division rate, so that, you know, you're always getting algae out of it. But in the same set of cultures, you could get 5 times the algae, you know, if you ran them at capacity. So the other, you know, the sort of in-between option is semi-continuous culture, where you remove a portion of the culture and replace that portion, let it grow, and do this over and over again. And, you know, this is the strategy that's worked for us, that, you know, we understand well, and we try to encourage people to give a try if they're doing batch culture. So, you know, there's a lot of advantages in terms of labor. And also you tend to get, you harvest, you know, if you harvest half, all you need to know is how long it takes to get back up to the maximum cell count. And so arithmetically, it's very simple. But also, if you have a perturbation, if it takes longer one day for this to come up, you can reduce the amount you harvest to compensate for that. So it's more active. It requires more attention from the operator, but it actually allows you to run the cultures more at capacity, production capacity, according to the light falling on your footprint or the amount of artificial light you're paying to keep on all day. So there's a lot, you know, a lot of advantages to this in those terms. But the other advantage is you can control whether you harvest log phase or stationary phase by, again, deciding when to harvest how much. So it gives you a lot of control. To pay for that, it takes more attention. So a few like other kind of random things. My joke about water quality. If you're taking seawater from a place with chemical toxicants, it's very difficult to solve that. And most of us take our water from, some have wells, but most of us take our water from surface waters that's full of competitors and full of predators of microalgae. So how do you deal with that? I mean, I could ask you all, and each one of you has a number of probably strategies you've used and some that you've arrived at. But Living contaminants is actually the first imperative, because you could be sunk. This is a culture with of Tetrasalmus with a bunch of bacteria. It's kind of hard to see with the lights on, but for every algal cell, we use the fluorochrome here. For every algal cell, there's probably 600 bacterial cells. That may or may not be sustainable, but for larvae even it can be kind of tough. This is a really interesting predator we had come into a large algal tank one time. It's an amoeba that in one day ate 20,000 liters worth of algae. Gone, and they were really happy. You see, they're all full. And this is that's heaven for amoeba right there. So this is a ciliate. How many of you have ciliates infesting your algal cultures? Yeah, so those are tough. Those are like the toughest one, and I'll tell you later how we got rid of those in our big cultures. And then we even get nematode infestations. This is from actually a local hatchery, not from one of our tanks. And so you got to treat the water somehow to remove all of these this zoo of stuff from surface waters that are naturally there to eat algae. That's part of the food web. It's not their fault, right? They're not trying to get you, but you're creating a wonderful situation for them. So filters of various kinds are commonly used. I'll tell you about this one in a minute, but how many people use bleach, chlorinate, dechlorinate? Yeah, okay, I mean, that's one way to go, but that's also a really touchy way to kill things in seawater. And like philosophically for me, adding poison to water that I'm going to use to grow living things, like, doesn't seem like a good idea. And it's both philosophical, and also I recognize that human error is rampant in everything every one of us does, me included, right? So we've tried to find alternatives to this. So the problems you run into is what it says on the label of the bottle is not always anywhere close. So when you do a dilution of it, or put a certain amount in water, it's hard to get that right every time. So you may not kill everything, or you may overkill everything. And then when you dechlorinate with thiosulfate, the first reaction produces sulfuric acid, and the second reaction deacidifies the water. And if you don't know how much bleach is there to begin with, and you don't match the thiosulfate very well, you could get very acid water, or have like a ton of thiosulfate there growing bacteria. So again, it's like, even if you do everything right, it's easy to make a mistake with chlorination, dechlorination. So an autoclave for a lot of stuff is great. We have a giant one. We can cook 4 technicians at once in our autoclave. But what we found that got rid of finally our ciliates and all of our living contaminants in our big scale cultures is this thing called capillary tangential flow filtration, or hollow fiber filters. And I love to tell the story about how I found out about this. I'm at a friend's house drinking beer on a Sunday afternoon, and he gives me a Miller Genuine Draft, which, I'm not quite the Dos Equis guy, but it's usually I don't drink that. And I'm sitting there looking at the label. It says cold filtered. And I'm thinking, the people I know that make beer pasteurize to stop the reaction, kill the yeast and everything. What is this cold filtered stuff about? So if you have questions about this beer, call this 800 number. So there I am on a Sunday afternoon on the phone to the Miller Brewing Company. I got some Genuine Draft in my hand. It says cold filtered. It said I could call you and get an answer. Oh yeah, that's our special way. They've got a sales guy, Sunday sales guy. So, I said, no, I'm a biologist. I need to talk to the engineer. So Monday morning, I'm on the phone with the engineer from Miller Brewing. How do you do that? He says, capillary tangential flow filtration. I'd never heard of that. What is it? So he explained it to me. The way this works is you pump the water in one end of this filter, and this is a plastic canister, and inside the plastic canister are a bunch of straws. The straws are the filter material. And there's a disc here that each straw is glued to, a disc here that each straw is glued to. So you pump water in this end, it goes through the straws, and it comes out the other end. So far, you've not accomplished anything. If you put pressure on the outflow, that puts pressure on the water going through all of these tubes, and some of the water seeps out. So, and if you set this at about half of the water flows through and half of it seeps out into the plastic canister, all of the particles that came in are carried out in the water that you don't keep. The water that you do keep in the plastic canister comes out through these side things. That water is sterile because you can buy these with 0.2 micrometer absolute exclusion filtration media. There's a whole bunch of hatcheries in the Northeast using this now. And all it costs you is you have to pump twice the water that you need to fill your algal tanks. And they require a little bit of upkeep. They need to be soaked in sodium hydroxide about once a week overnight to kill the biofilm that forms on the inside. But it's a great, great technology water treatment. It doesn't involve adding poison, and it doesn't catch particles. So you don't have to throw the filter away. The filter doesn't get ruined. It doesn't get filled and loaded. So you have to toss it, you know, and it doesn't clog. I have no idea. I mean, you just go online. We you know, buy them from a different supplier every time. Yeah, it's just like whoever has what we want, you know, on the shelf at that day. And the engineers at the companies can help you. They're going to say, you know, how many, you know, gallons or whatever, liters a day do you need? Like, you know, how many particles do you get? What kind of particle load? What's the turbidity of your water? They'll ask you a bunch of questions. Sometimes you have to go measure some things for them. You give them the answer and they design one. They decide how many of these capillaries, how long they need to be, you know, how big the canister is and all that stuff. They'll come back to you and say, okay, you know, here's one that meets your specs, and give you a price for it. And they're anywhere from $700 to $1,500 for, you know, for our outside culture, for example, is about $1,500. The one we have inside was about $700, and that one we have been using for 15 years. Capillary tangential flow filter or hollow fiber filter.
So if you put a disclaimer out there, can you give us a recommendation on where?
Google? Yeah, no, I can't actually. I'm in the Department of Commerce. I can't, you know, recommend one company over another. But I mean, you know, again, we bought them on purpose. I bought them from, you know, 7, 8 different suppliers, and they all are fine. They all work. The other downside of this is if you bump it and you knock one of those capillaries loose from where it's glued to the disc, the filter's ruined. So, you know, the people that have used them successfully bolt them to the wall somewhere, you know, out of the way, that you don't slam into it with a forklift or something. And you know, they last a long time. It's great technology.
What sort of volume per hour on your unit?
20,000 liters in 8 hours or 6 hours.
20,000 per 6 hours?
Yeah, the big one that we bought. But the beer guy said, he said, we, you know, we got a room with, you know, with 20-foot tall, 3 feet around, one's processing beer every day and all day, every day. Yeah.
On your 20,000 gallons, how much water do you discharge out of the filter to get to
20,000. We run it at half.
Okay. All right.
Yeah.
Do you pre-filter before?
Usually, yes. You know, usually we go through like a 10 micrometer wound filter first to get the really big chunks, because the internal diameter of the capillaries, if there's any particle bigger than that, it'll cover it. That's the, you know, the other thing you can ruin these filters. You can back flush them to get that stuff off, but you know, if you have a big chunk come in that's bigger than the internal diameter of a capillary, it'll clog it. So you just have to make sure the internal diameter is big enough for what your particle load is. That's something the engineers are going to ask you. Might ask you, would you rather pre-filter, or do you know, do you want us to give you a big enough internal diameter to pass the largest particles in your inflow? And they're accustomed to designing for manufacturing processes, not for environmental applications. That's why, you know, you have to kind of go back and forth with them a little bit, maybe measure a few things.
You don't replace the filter, you just back flush
Yeah, you back flush it and about once a week, soak it sodium hydroxide overnight. So it's not, if you have a continuous flow application, you need at least 2, because periodically you have to soak the biofilm off. It's a chemical, it's, you know, the dissolved organic in the water that glues itself to the surfaces after a while. Okay. So, you know, the other thing that was mentioned earlier that, you know, in my lab, we have a bacteriologist doing great work on probiotic bacteria. One of them that we helped develop is, I think, already for sale to hatcheries for oysters, not for clams. We haven't tried one for clams yet. And then there's another company that's evaluating one of our isolates. And, you know, if everything works out, they'll be selling that. We'll have 2 companies competing with each other with probiotic bacteria developed at the Milford lab. But that'll be a good thing, because, you know, having an option for treating larval bacteriosis is a good thing. And, you know, I won't ask this group how many people use antibiotics. It's illegal. But when you ask people, you know, the hands come up. So, you know, there's an alternative, you know, here, and I hope will be more widely used. And no, this is for larvae. Yeah, we haven't even gotten close to algal cultures. It's just, you know, like, how do you deal with with bacteria? You either exclude them, which you can't in big scale cultures, or, you know, maybe you protect the larvae from anything that might be in your algal culture by giving them a probiotic. And
You're purposely manipulating nitrosomas and nitrobacters.
Actually, one of the companies is selling a bacillus that upregulates immune function in larvae, and ours is a Vibrio alginolyticus with all of the toxicity genes knocked out, and that also upregulates immune function. So I skipped one, but because we have a whole thing tomorrow on chemical water quality, but this is, you know, just a reminder that there's a number of reasons to culture algae, and something we haven't done very well. And if you read the chapter I wrote like 100 years ago about microalgal culture, I said we have to do better using cross-industry stuff. And there's been, you know, a decade of algal biofuel research that I don't think the shellfish hatchery world is taking advantage of the findings there. So, you know, I'm trying to keep up with that literature and to get to know people in that industry to try kind of, you know, use some of the value from the investment that, you know, our country especially has put into biofuels, because I don't think we're going to be, you know, flying jets or driving cars on algal biofuels very much, but the advantages could be quite good for shellfish culture.